The name of this video is Properties of V. As it turns out, I'm not able to prove some of these properties for time reasons, but you must know them. The very first fundamental property of the electrostatic potential V is the following. Supposed to have a continuous charge distribution with volumetric density ρ in a specific region of space capital omega. Ρ is defined at any point capital Q, any source point capital Q, such as this point capital Q here. The capital Q points are the source points and can only live within capital omega. As always, my observation point is a point capital P in space. The vector distance in green, as always, between these 2 points is RQP. RQP. Great. We know from a previous video that the electrostatic potential V at point capital P for normal conditions at infinity is given by 1 divided by 4 pi epsilon naught. It's Columbian type volume integral on the region capital omega of ρ at point at capital Q times dV, which is my charge dq in the neighborhood of point capital Q, divided by, let's call it in general, RQP, the distance below here, which is the absolute value, the norm that is of this vector RQP. Okay, so the first rule tells us that if it so happens that ρ is a continuous function C0 in the domain, in the region capital omega, in addition, it is also limited in this region of space, that is, this region of space does not go to infinity, it's finite, that is limited, so it's continuous and limited, then in this case, it follows that the electrostatic potential function V at any point capital P in space is also a continuous function everywhere in space at any point capital P, which means anywhere you want. Note that this point capital P can also coincide with one of these charge points capital Q. So this is the first fundamental property, that is, the electrostatic potential is always a continuous function, whereas you remember from case 2 of the electrostatic, of Maxwell's equation for the electrostatic field, we know that the electrostatic field is not always a continuous function. For example, if I have a surface charge distribution with a surface density sigma, small sigma, in that case, clearly the electrostatic field is discontinuous across that surface. In that same case, the electrostatic potential remains continuous. It's always continuous. Don't forget that when you solve problems. When you need to stitch up V's for different regions of space, you need to stitch them up in a continuous fashion. If you see a gap in V, something went wrong in your problem. All right. Why is that? Well, it's kind of easy to explain why this is true when it's easy, very easy, when it so happens that point capital P does not coincide with point capital, with any point capital Q. That is, when capital P is always outside the region capital omega, it cannot coincide with any point capital Q. Well, under these conditions, first off, the integrand here, 1 over RQ, this follows that in the integrand, 1 over RQ, P, is obviously a well-defined function. Why is that? Why is it not ill-defined? It's well-defined because RQP is always different than 0. So I never have 1 over 0, which would be infinite, there would be a diverging, that is ill-defined integrand, there would be a problem. In this case, that cannot be. In addition, the fact that rho is a continuous function, so the numerator here is a continuous function, okay? The combination of these two aspects implies that the integrand is continuous and well-defined. The integral, even more so, has to be continuous and well-defined, because integrals usually soften things. So if this integrand is already very well-defined and all soft and smooth, the integral is even more soft and smooth. So this easy, not a problem there. The hard proof, which I cannot do for time reasons in this course, is when, on the contrary, it so happens that P coincides with one of these points inside capital omega. And in fact, there can be an infinite set of such coincidences, right? So when I observe within this region of space where the charge is defined, I can end up on an infinitesimal neighborhoods of any point on this region capital omega. So I can have an infinite of scenarios when, in this case, it happens that RQP is equal to 0, which means 1 over RQP happens to be ill-defined. Well, because it diverges, which means the integral is overall improper and is ill-defined. So in this case, even if rho is continuous. As it turns out, if you were to use Cauchy principal values, well, you will find out that for this type of integral, where the exponent is 1, which means it's smaller than 2, here, for an exponent smaller than 2, 1 over r, for example, actually, it could be equal than 2, so 1 over r squared would still work. For any function like this, where rho is continuous, and the integral is 1 over r to the power of 1, or actually also power of 2, like in Coulomb's law, for all these kind of integrals, Cauchy's principal value allows us to solve this problem of the ill-defined, and so you can show that even in this case, this remains true, okay? That's actually kind of the beauty of nature, because any function of the kind 1 over r or 1 over r squared falls in this category of functions which are improper integral, which lead to improper integrals, because they're ill-defined, but Cauchy's principal value allows us to solve that illness. And in fact, in the case of Coulomb's law, this is even more important, because Coulomb's law is 1 over r squared, okay? It's 1 over r squared. That's the last exponent that allows us to use this Cauchy's principal value to solve an illness. So in fact, if Coulomb's law would have been 1 over r cubed, we would have been in serious trouble, because the electric force is what keeps us together, our molecules, our particles together. If it was 1 over r cubed, everything would start to blow up and we wouldn't be here at all. So it's actually critical that these integrands of Coulombian type are at most 1 or 2. In the case of the potential, 1. In the case of the field, 2. Okay? That solves all these problems. So, bottom line, via P is always continuous at any point P, even within the region where the charge is distributed. That's the first key property of the electrostatic field. The second key property of the electrostatic field is that if ρ is limited, which we know it is in this case, and if, of course, we properly choose C to be equal to 0 in all our definitions, that is, we are considering a Green function with normal conditions and infinity, well, then it follows that always for a limited distribution, because it's limited. If I go very far away, it looks like a point-like charge in space. So it's a Coulomb law for a single charge when I look at it very far away. So the limit for, again, in this case, P that goes to infinity results in a V of P equal 0, okay? So this is the second big property. The electrostatic potential goes to 0 to infinity if ρ is limited. All right? Ρ is limited, and whereas here, if it's limited and if it's not, it's continuous. So continuous and 0 condition to infinity. The third important property you need to remember is that if I consider a line gamma that goes from point capital P1 to point capital P2, the work due to the field forces, so the internal work, to move a particle Q naught along this line is given by using the electrostatic potential Q naught times the electrostatic potential where? At the beginning, at the first point, minus at the last point. People usually do mistake and seem to think that is the last minus the first because of integrals, but because of the minus sign in the definition, it is like this, all right? And of course, it's independent of the line we follow to go there. We could use this line here, and we end up having always the same result. Lastly, the last property which is worth pointing out here, 4, is that the equipotential surfaces associated with V, they are always normal at each point on the surface to the field lines of E. Okay, so remember that, which is important, for example, in the case of conductors, which we are going to encounter soon. All right, so to recap this video, 1, if ρ is continuous and limited, V is limited, always. 2, when ρ is limited, the limit for p that goes to infinity of V of p is 0. V of p goes to 0 at infinity, normal conditions at infinity. The work along any line to go from P1 to P2 is independent from the line and is given by the test charge times the work of the internal forces, Vp1 minus Vp2, internal forces. 4, any equipotential surface associated with V is normal to the light. That's it.